Go ahead.
Okay. Good morning, everyone. Welcome back to the last lecture of the workshop of PWF Sudan, Expanding Horizons in Physics in Sudan, the second edition, about the density function theory methods and applications. Today's lecture will be given by our distinguished speaker, Prof. Omololu Akin-Ojo, the first and the former director of the ICTP IFER in Rwanda. And now he is a senior lecturer at the physics department at the University of Ibadan in Nigeria. He is also a member of the executive committee at the African School on Electronic Structure Methods and Applications. His research focuses on the design of new functionals for DFT and also the studies of water, semiconductivity, and electronic structure of materials. It's a pleasure to have you today, Professor, and you can share your slides.
Thank you very much. Yeah. Thank you, Allah. Thank you, Abubakar. Let me share. Okay, can you all see my slides?
Yes.
Okay. Obviously, I'm still here, but I'll turn off the video so that to save bandwidth. Okay. And first, I'd like to thank all the organizers for having me. So I'd like to thank Musa Hussein for having me, and also the other organizers, Tasha Stoic, and of course, I'll thank ICTP. I'll thank the people behind PWF, Physics Without Frontiers, and also thank you for coming. Okay, so I thank Allah also and everybody. So I'll be talking to you about machine learning in electronic structure, and I put this subtitle from theory to band gap prediction because this is really what you do for the hands-on today. So we're going to do a bit of hands-on with Python programming. I already have the Jupyter Notebook, so I sent it to Dr. Musa. So I think he should have sent it to you. Although I sent it late, so I hope you got it. Okay.
Yes, we received it. Thank you.
Okay, thank you. Yeah. So this is an outline of what we're going to do. So I'll start with okay. So what are we trying to do? Okay. So I'll start by telling you what electronic structure is, although you've had many classes and you already know about this. So what we're doing in electronic structure is like you are given a collection of atoms and nuclei. In this case, I show an example with zinc sulfide. Okay, the sulfur is the one in yellow, zinc is the one in gray. Okay. And given this arrangement, what we want to do is we want to predict properties of the system. For instance, we want to calculate the total energy of the system. This is the total energy. One of the reasons is important is it helps you to know which of the polymorphs of, say, zinc sulfide is the most stable one. So the one with the low energy is the most stable one. So if you have many polymorphs, for instance, carbon has many polymorphs, allotropes in this case. You want to know which is the most stable one, you can do it with DFT. So basically, you just start with a combination of the atoms, the nuclei and the electrons, and you try to predict properties. So one of the things you can predict is the total energy of the system. Another thing you can predict is the arrangement of electrons. So you can predict the arrangement of the electrons. So that's related to the wave function or the density. And you can predict other observable properties like the band gap, which we'll focus on as an example through this talk. Different optical responses like the things related to the refractive index. You can predict the magnetic properties of the system and other things here, like you can predict the density of the material, thermal conductivity. You can predict whether it's piezo or ferroelectric, and you can predict electrical conductivity. So, but you start with this structure usually, and then what takes you from the structure to these properties is this equation, which is the time-independent Schrodinger's equation, usually, okay? So anyway, the Schrödinger equation takes you from the left just the atoms and the positions of atoms to these properties. Okay. And people have been successful in getting this done. Okay. In particular here, I show an example where you can start with Schrodinger's equation and you can predict the band structure of the material. In this particular case, this is the band structure for the boring material, silicon. And it shows that it has a band gap, which we can't see in the scale, but it's like around 1 electron volt, say 1.14 electron volt, and it's an indirect band gap material. Okay, what this means actually is that it's not the best material for absorbing sunlight. Okay, but this we got it from solving this equation. Okay, solve this equation, you do some pre-processing, and you're able to do this. Now the challenge is if you have one atom, we can solve it for one atom, 1 electron, you can solve this. One atom with 2 electrons, it becomes more difficult. So there's no exact solution for the helium atom, for instance. So the only system we have an exact solution, atomic system that you have an exact solution for is the hydrogen atom. Any other system, you have an approximation. So even helium that has 1 nucleus and 2 electrons, we just approximate the energy, okay? And then not to talk of silicon that has 14 electrons. So we just approximate. And then also the box system, we approximate. So is the challenge to solve this equation, okay? But with the approximation we have, we're able to get good enough insights. So the approximation we usually use is nowadays is density functional theory, okay? So it maps the interacting electrons to non-interacting system. There's a term in the density functional theory called the exchange correlation functional, and only God knows the functional. So nobody, no human knows the functional. Everybody is guessing. Okay, educated guess, some guess more better than others, and everybody is trying. So we don't know the functional, but we know there are some theorems that tell us the functional exists, and if you knew it, we'll be able to predict all the properties of the material. The good thing about it is that if you double the size of your system, you only the computational expense only goes up by a factor of 8. So okay. But the bad thing is because we don't know the exact correlation functional, then our calculations are approximate. You can do better and get more accurate results by doing GW. GW is not an acronym. It just turns out that in doing the calculations, there's a term, the Green's function, that's multiplied by a Coulomb term, screening term, W. So G multiplies W, and that's why we call it GW approximation. Okay. So it's not green something, it's GW. Okay. But GW and then there's also solution of Bethe-Salpeter equation that gives more accurate results than DFT. But they scale like n to the 4th. So if you double the size of your system, instead of taking 8 times like DFT will take, it will take 16 times, okay, or even worse. Then apart from that, in GW, there's some parameters you have to optimize. So it really takes a lot of time and effort. So a calculation that would have taken you 1 week with DFT will take you, I mean, if you double the system and it took you 1 week with DFT, it will take you like 2 weeks with GW method. Yeah. But think about a case where you triple the size of the system, okay? And then with DFT, it will take you 27 times what you had before. With this one, it will take you 81 times. So anyway, the main thing is that this method are computationally expensive, okay? And if you don't have too many resources, then you limit yourself to small systems, and then you can handle many of the calculations. Okay. It turns out that nowadays, there's a way that you can get accurate results at the cost of DFT or even cheaper. Okay? And this is where this methods that people are introducing now is machine learning. So like we said before, electronic structure, DFT and GW are the workhorse of modern materials physics. They're expensive, If you have many materials and you don't, for instance, if you have many materials and you want a material, you have many hypothetical materials, okay, you're just trying different formulas, and you want a material that has a band gap of like 2 electron volts from all this, okay. If you are trying to do it with DFT or GW method, it will take you time to go through like 10,000 materials or a million materials, okay. It will take you time to go through 10,000 or a million hypothetical materials. But if you can use DFT, so if you can use machine learning, you will see that machine learning actually speeds up things. So like we said before, you can go from the crystal structure, you do DFT or GW or Bethe Zapata equation, BSC. It will take hours to days, and you'll be able to get a property, for instance, the band gap. So we are thinking of whether you can go directly from the crystal composition and get the band gap, okay? And use machine learning, and it will take milliseconds instead of hours or days. So you'll be able to do like 10,000 evaluations or even a million compounds, hypothetical compounds, with machine learning, which you cannot do with DFT or GW in a reasonable lifetime. So we are hoping that one can go directly from just using the crystal structure and predicting the band gap or other properties you want to predict using machine learning. I focus here on band gap because it is one that is very common and also one that I've done myself. Okay. So before I tell you exactly more about machine learning, I'll try to give you an example that you can relate to. Okay. So instead of solving Schrödinger's equation like we have here, a simple thing could be that let's suppose that the band gap, so the band gap is the difference between the conduction band minimum and the valence band maximum. So suppose that band gap, which we don't know, suppose you can write it as a linear combination of these properties, okay? So we write it as a constant, A naught, plus another constant, A1, times the mean of the electronegativity. So Pauli a long time ago gave each element a value for electronegativity to tell us how strongly it attracts electrons when it's forming a bond. So fluorine attracts electrons like crazy. So it has the highest electronegativity. Cesium, which is like 3.98 or 4, okay. Cesium hardly attracts anything, so it has a electronegativity of like 0.79, okay. And then there's a range in between them, okay. So if you have a compound and 2 atoms have the same electronegativity, then the difference in electronegativity is 0, then none of them will attract the electron from the other one. But for an ionic compound, okay, you have one that has a small electronegativity and another element that has a larger electronegativity. So the one that has the larger electronegativity will draw the electrons from the one that has the lower electronegativity. So when the electronegativity difference is large, then you are likely to form an ionic compound. And if you're an ionic compound, the electrons are bound and you are likely to be an insulator. Okay, so it makes sense to think that the band gap correlates with the range of the electronegativity. Okay, so if the difference in electronegativity of a compound is large, then it's likely to be ionic, and if it's ionic, then it's likely to be an insulator, so the band gap will be wide or large. Okay, so it's possible. So you can think that the band gap depends on some simple properties, okay, like the mean of the electronegativity. So if I give you zinc this compound, like we had before, zinc sulfide, then you can calculate the mean electronegativity. So you take the electronegativity of zinc, you add it to twice the electronegativity of sulfur, and you divide it by 3. Okay. So you can do that. To find the range of the electronegativity, you just find electronegativity of zinc minus the one of sulfur and the magnitude. So you can do that. So I can do this because there's a table of electronegativities. I can do this without doing too much computation. Also, you need the covalent radius, and there's a table, you can look it up on Wikipedia, of covalent radii. Okay, so these properties are properties you can get easily, okay, without doing too much calculation. So even in high school, you could just have done it. Okay, so suppose the band gap depends on these these properties, electronegativities, the mean electronegativity, the range, the standard deviation. Let's say it depends also on the atomic number, the mean of the atomic number. You can think it depends on the mean of the covalent radius. Okay. You can think it depends on the mean of the number of valence electrons and different other things that you could think of. So you can keep increasing it to A7, A8, A9, some other properties that you can think of. Maybe you can think that it will depend on whether the number of electrons in the system is odd or even. Okay. Yes, because we already know that if you have a system and the number of electrons in the unit cell is odd, then this material will be metallic. Okay, so you can add A7 times the even or oddness of the number of electrons in the unit cell. So you can form something like this. Okay, so I'm telling you about a simple machine learning model. Okay, so each of the variables E and Z, they're easy to calculate. Okay, these variables on the right, En mean, En range, En standard deviation, Z mean, and any other property that you have there, they're called descriptors, or some people call them features also. Okay. Now, if I want to get the band gap for a material, how do I get the band gap? I take A naught, which I should have. I multiply A1 by the En mean that I'll calculate for this material. I also calculate En range and multiply by A2. En standard deviation and multiply by A3, and all this I'll multiply it A7, A8, whatever you want. So I do this calculation, and this should give me my band gap for the model, and hopefully is the correct band gap. Okay. One problem is how to get the coefficients AI. Okay, A naught, A1. I've not told you how to get that. En, you can easily get it, like I described. But A naught, A1, A2, how do you get it? Okay. So that's the first problem. I'll show you how to get it in the next slide. Another bigger problem is whether this formula will work. You know, maybe the band gap depends on the square of the standard deviation, not linearly on it, right? Maybe it depends on the product of this En and the parity of the number of electrons. Maybe it depends on product of this En and the mean of the number of valence electrons. This model that I have is too simple, you know, and it doesn't have such products and things like that. So that's the bigger problem, whether the assumption is true. Okay, but let's say there are ways you can mitigate that. Okay, but let's say we just assume this model. Still, you have to find A naught, A1, A2. Okay, so how do we do that? The easiest thing to do that is to get some data. We already know the band gap. So I'm showing you some data that I took from Wikipedia where you already know the band gap. So this is aluminum nitride. This is carbon, as in diamond. Okay. This is silicon, germanium, gallium nitride, gallium phosphide, and many other ones. And the band gap is known. Okay. So you can put the band gap here, and all these properties, En mean, En range, you already know them. So if you have exactly 200 band gaps and you have exactly 200 you have exactly 200 band gaps and you have exactly, sorry, suppose you have okay, let's take this case where you have up to A6. Okay, so suppose you have 7 band gaps. Okay, then you can solve these 7 equations. Okay, so you have this line for one material, you have another line for the next material, another line for the next material. I have exactly 7 of them. Okay, and you have 7 coefficients, A naught, A1 up to A6. Then you can just solve the simultaneous equation. Okay, and find A naught, A1, A2. Okay, but in this case, actually, you will have many more compounds, and one thing you can do is to find the difference between the experimental band gap that you have here and the one that the model predicts. You square them, you sum them, you take an average, and you try to minimize this difference. Okay. So this is called just you calculate the chi-squared and you minimize the chi-squared. Okay. So if I had a list of compounds and the band gaps like I have on my left, then I can choose the best set of AI to target the band gaps. This data is called my data set or training data. Okay, so in machine learning speak, we say training data. And then you choose the best set of AI to minimize this chi-squared. Okay. So this is the simplest machine learning model called linear regression. Okay. Okay. So why is this helpful? So yeah.
Excuse me, Professor.
Yes.
Can the participant ask you questions during the lecture?
Absolutely. Yes, please.
I have a question. How do you obtain the N train?
Oh,
in the formula?
So, yeah. So N train is just the number of compounds that you have in your training set. So if you go on Wikipedia, for instance, they give you a list of some compounds. Okay. There's a paper, this is a good question, which I don't show here, but there's a paper from Journal of Chemical Data that has like, I don't know, more than 700 compounds and their band gaps. Okay. So in that case, if you use 700 data points and then the band gap, then entry will be 700. So you can just go online and people have graciously calculated or done experiments to get the band gap. So this is what will be here for the band gap of the experimental band gap. And then your model, you use the model above, and then you try to find AI. So the AI will be in this model expression, and you try to find the AI that will minimize this chi-squared. Okay. So basically, people already have a lot of experimental data to use. And people are calculating GW data that we can use also. DFT data, a lot of people have calculated it also. So we can have that and we can train a model to do this, to find AI. So this is the simplest model and is linear regression. So
I also have a quick question. So
yes.
considering the A0, A1, and all these parameters, are they like similar for all the materials, or they are different for each materials?
Okay, so this is a good question. In this example, we'll just say that, okay, they will be different for each material, but you will find the best set that works the best for all the materials. So this is why we have a chi-squared here. And you try to minimize the chi-squared and your model. So I think I have, okay, I'll show you a picture later on where you see that you may not get exactly, so that your AI will not be the same for every material. But if you minimize chi-squared, then the difference for all the materials will be small, if you are lucky. Okay, so they'll be different for each material in principle, but if you are lucky enough, you can minimize chi-squared, okay, and make sure that the error that you get is very small. Yeah, I hope this answers the question.
Yes, so at the end, you will have a set of AI that minimize chi for each material.
No. You minimize chi-squared for all the materials that you have, not for each one. Yeah. You have to do it so you take like, I don't know, maybe 7,000 materials and you already have the band gap and you minimize chi-squared for all the 7,000. Okay. So you do that once and forever. Then when somebody brings you a new model, so I bring you a new compound, say gallium fluoride. I don't know if this exists or not. Okay. You bring a new compound, GAF, and you say, what's the band gap of this material? Okay. So all I have to do is, even though GAF was not in my training, okay, all I have to do is I have the A0, A1 up to whatever. Then I'll just use this model because I can calculate this EN mean, EN range, all these features. I can calculate it for gallium fluoride. The A0 that I got from training the 7,000 compounds, I put it in here, okay, and then I predict the band gap for gallium fluoride. Okay, so this is what you do. So you train, and once you train, then if I give you a new compound, you featureize this. That means you calculate the electronegativity difference and all that. Then you combine with the parameters AI to obtain BG from the equation we showed above. Yeah. So if you're lucky, it works. If you're not lucky, it doesn't work. Okay, but we test before we say that it works, and then you give an error estimate to say, okay, maybe your error estimate is 0.2 electron volt. So then if you use the model, we think within 0.2 electron volts, your answer could be correct. Okay. And the reason why we use machine learning is people have shown that machine learning can recognize patterns that we cannot recognize. So electronic structured data contains hidden relationships. I'll show you one later on. Okay. And then if this model works, for instance, this one I'm showing, then we can replace expensive DFT, GW calculations with fast machine learning predictions. And then you can use it to screen thousands of materials. So, I can write thousands and thousands of material formulas, okay? And I don't even know whether they're stable or not. Like GAF, I don't know if it exists or not. I can just write anything. So you have like 100 elements. So to form binaries, you have like so many ways of like 100 times 100 over 2, like binaries that you can form. Not to talk about changing their stoichiometry, which you can change also. So they're just like, that one will give you 100 times 100, like 10,000, okay? And then you can go ternaries, you can have millions of them. Quaternaries, you can have 100 millions of them. So there's so many combinations that you can have, okay? And you can just rapidly screen them by using this machine learning model to say, okay, is it, let's say I want a material that has a band gap of 1.2 electron volts. Then I can just screen these many formulas I'm writing, okay? And then see which ones give me 1.2 electron volts, okay? Also, you want to know whether they're stable or not. You can develop machine learning models to predict stability also, and then you run it through the stability to see whether they're stable or not. And then you can keep doing different things like that. And then the few that you get, then you can say, okay, now out of the 1 million that are screened, there are 10 that have the right band gap, and my machine learning models also predict that they're stable. So now let me do DFT calculations on them. So then you do DFT or GW on just 10 instead of a million. And then those 10 now, you can, after you do GW calculations, maybe 5 of them survive or 3 of them show the properties you want. Like maybe you want a band gap of 1.2, maybe 3 of them have the band gap of 1.2 and they're stable. Then you can do experiment just on 3 instead of doing experiment on the million. Okay. Okay. The question that was asked before, like the AI, do we develop them for each material? No, you develop them a set for all the material, and you hope that it's transferable, that the data you develop, once you develop for a particular set of data will be useful for any other system that you want to use it for. Okay, so the main goal in machine learning is to predict material properties directly from atomic structure. Okay, so apart from the linear regression that I told you, which is the simplest, and you can interpret it very well, I'll show you how to interpret it. So for instance, you can normalize EN mean, EN range, you can normalize all this. If I find that the coefficient for EN standard deviation normalized, A3 is the largest, then I think this EN standard deviation contributes the most to the band gap, okay? So you can easily interpret it this way, depending on the size of the coefficients. So there's linear or polynomial regression, and there's the simplest, and it's quite interpretable. If the data is non-linear, then you get poor results. There's another one called random forest, which I won't say much about, but it's really a black box, okay? They support vector machines, which is easy to understand also. I won't go into this, but it scales poorly with the number of data that you have. Okay? The most common one nowadays is neural networks. Okay, so neural networks, what people do is they feed a neural network with the data. The neural network does some convolution of your data and it spits out the result. So it really does some non-linear thing with your data. So instead of linear regression, neural networks really just does some non-linear regression, more or less, okay, and outputs the results, okay. But you need a lot of data for it. That's a problem. There's kernel-ridge regression, which is almost like linear polynomial regression, but it allows you to use not just a linear combination, even products of those combinations. Then there's the Gaussian processes, which unfortunately Gaussian processes I don't know much about. Okay. For your exercise, we use linear regression and random forest. Linear regression is easy, and for a 2-hour lecture, I think we can easily understand it and explain it. Random forest, you can explain it also. You need a forest, you make decision. Okay, so you use decision trees, and then you can do that. Okay. Okay, now
I have a question. Can the same formula be used to find other properties, or it's only for the band gap?
Oh, good question. Yeah. No. So for other properties, you try a different formula, but maybe based on the same thing. So you have to find a new set of coefficients, because the properties will be different. So you will need to get a new set of data here. So instead of band gap, let's say what you want is the energy, relative energy. Then you have to put the relative energies here and try to fit the relative energies. Okay. So you try to find the coefficient also to fit it. For that case also, maybe these properties are not the best properties, and you have to find other properties, other descriptors. Another one is that people have been doing is to find the thermal conductivity of a material. So instead of band gap here, there will be thermal conductivity, and then they can try to experimental thermal conductivity, and then you can try to predict it. Okay, but you have to train it for that particular one also. Okay, so for different properties you want, you have to do a training. Okay, yeah. So like I said, linear regression is the simplest. Okay, there's random forest, which uses decision trees that support vector machine. Neural networks is the most common now, but you need a lot of data. Okay. Then there's kernel ridge regression, which is in effect kind of extending linear regression, but so that you can use products. Okay. Gaussian processes is there also. I don't know much about that.
Okay. There is also another question on the chat by Doha. She's
Yes.
asking, does the training data set need to have specific characteristics related to the target material?
Okay, actually, in people that do machine learning, it does not have to have any direct relationship that you know of, because many times we don't even know what is related or what's not related. Okay, it's not so easy to know if they're related. Sorry, I wanted to show you a picture, but I don't have it here. Yeah, I wanted to show you a picture. If I have time, I'll look for the picture. Okay. So it's hard to know whether a property is related to the band gap or a descriptor, whether it's related to your target property or not. It's hard to know. Okay. One thing you can do, yes, you can plot your predictor against the target property. Oh yeah, we'll see it when we do the exercise, you'll see it. Let me see if I can go there now. Sorry, let me see if I can go to. Okay, maybe I can go there now. Yeah, you are going to see that. I think you can see my screen. Yeah.
Yes, we can see your screen.
Okay. Okay, yeah. So here you'll do it later, but let's spy on what we have. You will see that. Okay, so here you do the plot also of band gap against electronegativity difference. Okay. You may not think about it, but if you look at it now, you see that it seems as if there's roughly linear relationship, okay, between the experimental band gap, and on the horizontal axis, what you have there is the electronegativity range. Okay, so it seems that there's a upward trend. Okay, not so clear, but it seems there's an upward trend that as the electronegativity range increases, the experimental band gap also increases. Okay, whether you know it or not, you could just have done machine learning, and machine learning should be able to help you to find the pattern. Okay, so you don't have to know that there's a pattern. Okay, in fact, this is one reason why machine learning is good. It helps you to discover the pattern. It should help you to discover the pattern. So whether you know or not, you can just put everything together, and then at the end, I'll show you the way to do it. It can help you to know which features are most important, and yeah, it can help you to know the features that are most important. So at the beginning, you may know, you may not know. It's good the features you know already to put it in, and that it's good that the features you know are important, you put it in, okay? And then other features you put in also, you know. For instance, for superconductivity, we know that if it's electrophonon superconductivity, we already know that the heavier the mass, the lower the TC. Okay. So it seems that TC, the superconducting temperature, depends on the mass. So it's important, okay, to put in something about the mass. Okay. But even if you don't know, you can still throw in everything that matters, and those that do not matter, you put it in. And then machine learning should help you to know what is important, what is not. Okay. Nihad has the hand up.
Yes,
Yes, I have question. If I have two materials with the same composition structure or descriptives, what will be happening? Like, for example, diamond and graphene are both from carbon, and they have the same structure.
Okay, this is a good question. Like you can have carbon and diamond and graphite, right? And you're trying to predict a property like the thermal conductivity or the hardness. Okay. It turns out that the thing I've shown you here is too simplistic. Okay. It's not, so using the chemical formula is not enough. You need also to have a column that uses the structure. Okay. So then, so in here, you should have a constant, A7, and something that has to do with the structure. Okay. And then another A8 and something else that has to do with the structure, because we know the structure is important. So we should add structural properties to this one. Okay. Yeah. But for beginning, okay. Oh, yeah, this is what we can do. And then later on, you can improve and add structural properties to it and see if it improves or if it doesn't. For superconductivity, it turns out that in the past, some people, they have a table of like 23,000 compounds. Unfortunately, only the chemical formula is there, and they have the TC of those compounds. So many people have been using this data to predict TC, okay? But like you said, okay, you don't know, there could be two different forms of the same thing, or I'm sorry, two different forms of the same elements, and their TC should be different, and how do we know? So some people are now saying, okay, let's now do calculations that includes the structure, and then for the same chemical formula, we can have different structures, and then we can have different TC, and we can include this in our data set. Okay, but you see later that this is one of the problems of machine learning with electronic structures. We don't have enough data. Okay, so we need a lot of data, including data that has not just the chemical formula, but also the structures. And if you include that, then we think we'll get something better. Okay, good question. Yeah. Okay. So here I'll tell you formally what machine learning is after giving the example. So it's a study of algorithms that improve through experience. You don't have to formally code the behavior in machine learning. Okay. So machine learning is just algorithm that build a mathematical model from the data. So like we said, the coefficients A0, A1, blah, 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 you build them from the data that you have. Okay. And you don't explicitly program those coefficients yourself. The other thing is we don't explicitly program the underlying physical law. So I'm not saying that band gap depends, like this is the formula for band gap. No, I can't derive this, right? There's no derivation for this. But we just guess and say maybe it depends on this, and then we try to find the parameters. Okay, so you don't need to know the underlying physical law. Okay, if you know the underlying physical law, it's better. Okay, and if you can think of the things that your property to, that's even better. Then you can throw it in, and hopefully it will give you a better model. Yeah, but in principle, you don't have to know all that. You can just throw in whatever you want to throw in, It turns out that some people, they've developed codes that if you give the structure and the chemical formula to the codes, they will find like more than 140 possible features for you. Just different combination, like electronegativity, the mass, the magnetic moments of the atom, the size of the atom, the ground state energy of the atom, the thermal conductivity of the material. You know, they just put a bunch of different things together because we don't know, right? So this is one way that people do. Okay. Everything I've been describing to you is called supervised machine learning. Okay, because in supervised machine learning, I give you the target, so you know the band gap you want to get, and I provide for you the chemical formula or the structure. Okay, so I label my data. I already tell you this is the band gap. Okay, and you want to predict the band gap. There's another aspect which is unsupervised machine learning, in which I don't label the data. Okay, and machine learning can help to put labels on the data itself. This is usually good for categorization. Okay, so you have the data, and it turns out that unknown to you, you can actually group them into clusters. Let me give you an example. So in the case in which I have materials with the band gap, before I do the training that I'm doing, I can first use unsupervised machine learning to cluster them. What do I mean? Machine learning can help you to know that, okay, this one's ionic, we put it in a cluster and we develop a model for ionic compounds. These ones are rare gas, behave like rare gas, we put them in another cluster and develop a different machine learning for them. These ones are oxides. You know, you don't have to know yourself that is an oxide, okay, or oxide-like. Machine learning can help you to cluster them unsupervised. So it can help you to cluster them unsupervised. And then for each cluster, you can now use a supervised machine learning model. This is possible. So you don't have to have labeled data. Even if you have the data that's not labeled, machine learning can help you to cluster them. So it depends on what you want to do. Yes, if you want to find a band gap, yes, you need to have a label. But even when you have a label, you may want to cluster them first, and machine learning can help you to cluster them. And when you cluster them, you don't have to cluster them and say, okay, anything that has an oxygen is oxide, I cluster it. Machine learning can help you to find the right cluster. It may be compounds that have oxygen or compounds that have sulfur. It can cluster them together because you know oxygen and sulfur are in the same group of the periodic table, so it may cluster them together. Okay, so there's a way to use machine learning. They call it unsupervised machine learning, to cluster and find common features and put your data into groups. So this is an example of unsupervised machine learning. So it can help to find structures that you didn't know in your data. Okay. There's reinforcement learning also. Reinforcement learning typically also you may not label, but the machine learning model itself will learn that this is a good way to follow. The way you do it is when it achieves what you want it to achieve, you reward it. Okay. And then when you reward it, the next time it tries to maximize its reward, then it knows which path to take to maximize the reward. Okay. Maybe another time we can talk about reinforced machine learning and unsupervised learning. Okay. But for this one, we just focus on the supervised machine learning as a first step in machine learning. Okay. I've told you about sorry, please hold on. Okay, so I've told you about features. Those are the input descriptors which you get yourself. The target properties. So for instance, it could be band gap. Okay. Later you will see that when we have all this data, we are smart not to use all the data to do the training, because if you use all the data to do the training, then you don't know how good your model is. So what we do is we split the data into a set that we call the training data. and we use that to develop the parameters of our model, maybe A0, A1, and all that. And then on the test set, we don't develop a model for them, but we now use the test set to check how accurate our model is. So our model never saw the test set. So it did not develop A0, A1, and all that for the test set, but it did for the training set. So after we train, we now use the test set to calculate, to predict, and we compare it with the correct answer and see how well it did. So in this case, it's not like we trained already and then you are just predicting after you've used the same data for training. So we split. You'll see later how we split the data into training and test set. Okay. So this is the pipeline for supervised machine learning. You take the data from a DFT database or from experiment. You add your features, so they call that featurizing the data. Okay, and then you train. Okay, you train and you validate. So you train on the training set, and then you validate on the test set. Okay, and then once you've done this and you are satisfied that you think the error in your test set is small enough, then you can use it to predict new materials. Okay, where do you get your data from? It turns out that some people have graciously given us a lot of DFT data. Okay, experimental data are not many, but DFT data, you know, while we are talking now, you can have your computer calculating and doing the calculations. Okay, experiments for now, they're expensive and people have to be there for the most part. Okay, so but calculations, data from calculation from DFT databases, there's a database called Materials Project. Okay, online, if you just make a Google search for Materials Project, you see the database is there. There's one called Aflo from a group in the US, Stefano Cutarolo's group. There's OQMD also. There's a new one now, Jarvis DFT, maybe not so new. Nomad also is there. Okay, so all these are databases that you can get DFT data and DFT data from. Okay, Nomad also has GW data. I don't remember if Jarvis also, it says Jarvis DFT, so it probably doesn't have GW data, but Nomad has GW data. Apple is really DFT data. Okay, so you get the data. People have also developed models that if you give it the chemical formula, that's the composition and the structure, it can give you a bunch of features. So it will just, features that you may not even think of. So it will just calculate the features for you. Okay. And then when you train, you can pick a different models that like we showed here and use the different models to train. Again, people have developed methods. There's a code called Lazy Predict where it takes your data and it runs through like 40-something models. Okay, so there are more models than I have shown here. Okay, these are some of the common ones, but people have developed codes that it will take like 40-something models and run your data through each of the models. At the end, it will tell you your loss function, that's like your chi-squared, and it will also tell you how long each calculation took. Okay, then you can use it to see which is the best model to use for your data. So people have with Python, in the Python community, people have developed featureizers and a code that can help you to quickly run through many models. Okay, and then this one you have to do yourself. So what I did one time with a student, we wanted to predict TC for binary compounds. So I just told him to juxtapose two elements together. So for instance, sodium and carbon, and he should go from sodium 1 to 6 and carbon 6 to 1. Okay. So it will be sodium 1, carbon 1, and then sodium 1, carbon 2, sodium 1, carbon 3, like that. And just, so it generated like, I don't know, maybe thousands of them. And then we now use machine learning model to predict TC, and then we just ranked to see which one has the highest TC. Okay. And unfortunately, we don't have the structure. We only have the chemical formula. So we have to start guessing what the structure was for a particular one that we saw that had a high TC. Interestingly, our models predict, like people already know, that hydrides have a high TC, okay? Because the hydrogen is the lightest atom, so the TC is high, because TC superconducting temperature is proportional to, for electron phonons, is proportional to 1 over square root of the mass. So hydrogen has the lightest mass, so it wasn't surprising that our model predicted many hydrides. So we decided, okay, people already know about hydrides, and then we looked among the other ones, which one has a higher TC. We found one which is not magnesium diboride and has a high TC of like 36 Kelvin. Okay. And after we saw it, the chemical formula, we started trying different things because we don't know the structure. You know, the superconductivity data that I told you has only the chemical formula. So we didn't know what the chemical right structure was. So we were trying different things. We tried some that gave us like 5 Kelvin, 3 Kelvin. And then he tried one that gave him like 30 something Kelvin. So we are happy about it. Okay. Okay, so for today's hands-on, we are going to do a toy one, and then after that, we are going to try to do a prediction for machine learning to predict band gap. So I already told you about the definition for the band gap. So it is difference between the conduction band minimum and the valence band maximum, and it's important for photovoltaics, optoelectronics, semiconductor physics. In photovoltaic also, we want to know whether it's a direct band gap or indirect band gap. This is important too. So, but in today's work, we will just try to predict the band gap. So the features we use the mean electronegativity difference, mean atomic number, average ionic radius, valence electron count. I don't know if we use this row group statistics. Our target will be the experimental band gap, because and then we will use linear regression first, and then we use random forest. Our metric, we'll use the mean absolute error. The one I showed you, the chi-squared, is actually the mean squared error. Okay, but we will report also the MAE. How good the data looks on the whether it matches a straight line is related to R squared. We'll see. We'll look at that also. Okay. This is an illustrative example. Okay, this is not what you will see in your calculations today. So here, on the horizontal axis, you are plotting the true band gap, and here we are plotting the prediction from an illustrative prediction from the model. The mean absolute error is 0.3 electron volt in this case. Okay. So this may be good, this may not be good. If you compare it to DFT, like PBE, the error is like 1 electron volt on average. So getting an error of 0.3 electron volts seems to be something that is good. So this is just an illustrative thing in an illustration, but this is not the real case. We'll do the real case in a few minutes. Okay. So instead of predicting the band gap directly, okay, some people have found that you can predict the difference between DFT and the band gap. Okay. Some will say, but DFT is slow, yes, okay, but not as slow as GW and not as computing intensive as GW. So let's say your target is GW, okay, or experiment, and you can still afford DFT. So you can calculate the difference between the experiment or GW and DFT, okay, and then so this error is what you will now predict. You don't predict the whole DFT band gap, but you can predict the error. So this is another strategy, and it seems to be a smarter strategy. So you don't have to predict the whole band gap. You can predict the difference between the experimental band gap and the DFT band gap. Okay. And then when you give me a new material, what should I do? First, I calculate the DFT energy. Then I'll use my model, my machine learning model, to predict the difference, the correction. I add the correction to my DFT, and this should give me a better band gap than if I try to predict the whole band gap from machine learning. So people found out that this works better. And there's a reason why it works better. The difference varies more smoothly and also needs less data to learn than EG itself. Okay. The hard physics is already captured by the DFT. Okay. A recent work that I did was to say, instead of using DFT, can I use the semi-empirical model? Okay. So here I found the difference between what did I do? Yeah, I found the difference between hybrid DFT and my semi-empirical model, and I fitted that. Okay. And then that was what I added to the hybrid model. The hybrid model is cheaper than DFT, so I did it. Okay. And the result were, I'm trying to think, my error was like 0.2 electron volt. Yes, correct. Okay. Like someone asked, which features should we include? It turns out that after you do your develop your model, there's a way to ask the machine learning model to tell you which features are most important. Okay, so here, so if you use random forest, okay, which we'll see later, then you can ask it to give you a plot like this. And on this plot, on the horizontal axis shows the importance, on the vertical axis shows the different features. So in this case, the range of the electronegativity, delta chi, was the most important, followed by the mean of the atomic number and the number of valence electrons. So you can use machine learning to ask for, you can ask machine learning model which feature is most important. This feature importance, we use it when you have random forest or a tree-based model, okay, like random forest. Okay. It gives you a feature importance score for free. Okay. Once you do the model, the feature importance, it calculates the feature importance for each property also. And like I mentioned, this is exactly what you expect, even if you didn't know any chemistry before. Okay. That the electronegativity difference and bonding character, they dominate. I mean, you find in this case that the electronegativity difference dominates. And this is consistent with the fact that you know that if the electronegativity difference is large, then you're likely to have an ionic bond. And if you have an ionic bond, then this is likely to have a large band gap because there are no free ions. Sorry, there are no free electrons moving around. Okay, so it's very likely not to be metallic. So you can find this from machine learning. Let's say you did linear regression. If you scale all your features, then the coefficient of the scaled feature, the size, helps you to know which features are important. The ones that have the highest magnitude is the most important one. Okay. Then I tell you a little bit about challenges and pitfalls with machine learning. The first thing is data is scarce. Reliable experimental data is quite scarce. Okay. High level theory, you know, is scarce, like to have GW calculations. But one thing I'm thinking was sometimes I have my machine that's just idle. Why don't I just be running GW calculations while I'm on the beach or doing anything? You know, it's just running the calculations. This is an idea, like if you automate it and while you are sleeping or while the sun is shining, it's doing the calculations for you. So maybe within a year, you can get up to like 1,000 data points for GW. Okay. The DFT has a problem because DFT band gap are typically smaller than the experimental band gap. Okay, so this is a problem that shows up, that is introduced when you develop your basis set. Okay. Some people believe that these models they interpolate. So if you give it something that's too far out from the training set, then it will not give you correct results. I'm mixed about it. I don't know if I should say yes, definitely, or no. For some cases, yes, it's true. For some other cases, I feel like the machine learning should learn enough to be able to even predict for those materials. But take a case where you use many compounds and you never include an oxide, okay, for your training. Will the machine learning model be able to predict the band gap, for instance, of an oxide? Some people will say yes, some people will say no. That some people will think yes, it should be smart enough to, because it really does not need to know whether it's an oxide or not. It just needs to know the electronegativity and some other properties of it. So some people will think it will work, some people think it does not. Okay. Sometimes we've not built into our models to know limits or symmetries. For instance, some people want to do something like maybe CaC2 or Ca2C4. Okay, those could be the same compounds, but then some machine learning models may not know that they're the same compounds, and it may calculate different things for them. Okay, but I think for the most part, many models we have already will know that CaC2 and Ca2C4 are the same. Okay. So beyond band gaps, people are using machine learning for different things. Okay. People are using it to develop force fields, so that instead of using force fields from ab initio calculations, people have developed gap, maze, grace, network models, and you can use this to do your molecular dynamic simulations. It will give the energies and the forces at a fraction of the cost of DFT. People are using machine learning also to develop better X-ray correlation functional. People are using models that other people have developed to screen batteries and solar cells and catalysts. Okay. A new one is where people are generating new models. They just propose new crystal structures with target properties. So you have a property and then you try different things to see which one gives you your target property. Okay. Definitely machine learning will not replace our jobs as people that do electronic structure theory, but it can accelerate it and it can augment it. Yeah. So this is the summary of many things I've said. And then I hope we can go to the hands-on now. If you have questions, more questions, I can take them, and then we can go ahead.
Thank you for
Thank
the
you.
lecture.
Yeah, sure.
So I have a quick question. So
Yes.
the first thing, so you have talked so far about the gap that machine learning can estimate for us.
Yes.
So how good it is, let us say, compared to the one we measure at the experiment. And
okay.
Yes, and another thing concerning for example, the model that you have given for estimating the gap, that equation that contains these parameters AI.
Yeah.
So how usually people like write these models, like what is the criteria to write such model? I know that it is not the only one. You can have more depending on the if I understood well, depending on the data that you have, right?
Okay, yeah.
So how usually, what is the strategy in order to write such a model for calculating certain properties that you want?
Okay, yeah. Thank you very much. So I'll answer both questions. So the first thing is, you can get an error as small as 0.2 electron volts. Okay. Not if you fit the band gap directly, but if you do this delta machine learning model, okay, this delta machine learning model, so you fit the difference between experiments and some DFT calculations, you fit the difference. So you get this correction as a model, and then you can now do DFT and add the correction to it. So this can give you an accuracy of like 0.2 electron volts. Actually, one that I did, which was not even as great as that, I just took good enough DFT. They were hybrid DFT calculations. That was my reference. And then I subtracted the semi-empirical. I did calculations with the semi-empirical model. I subtracted, And then I developed a model for that, for the correction. When I add the correction to my semi-empirical model, I have an error of like 0.2, maybe 0.24 electron volt for the band gap. Okay. So I think with DFT for this band gap, it's reasonably accurate to say you can get at least 0.2 electron volt. You can improve your model to get more. Okay. Now, yeah, let's talk about the model that I gave to you. Okay. You know, I felt like we are starting with machine learning. Okay. So it's not like you're an expert in machine learning. So this linear regression is like the simplest one that anyone could have. I'll be honest with you, almost nobody uses it. Okay. So I just do it, and we will do it online in the hands-on. Okay. And you'll see how good or how bad it is. Okay. Almost nobody does it. Okay. But whichever machine learning model you use, there are some parameters in it, maybe not exactly the same like this, but there's some parameters in it that you optimize to train your model. Okay. And those parameters, they couple also with different properties, different features, okay, in different ways. Some are linear, some are non-linear. Even if you use a neural network, it couples with the properties in a non-linear way. So which properties should you use? It turns out that the materials project people, they've developed some codes that if you give it a chemical formula and structure, it's going to generate for you many properties, even properties that you will not even think about yourself. So they've already done it. I'll try to find a page where it lists a bunch of properties for you, maybe up to like 140 properties. So you can start from there. Okay. And then whichever model you have, typically will have some parameters. It may not be linear like this. It may include products, or it may not even be like this. It may be like neural networks. But neural networks also have parameters, and these parameters have to be determined to minimize chi-squared. So everybody tries to minimize chi-squared. The model may be different, okay, but we try to minimize this. And this your model will contain the parameters of the model. Okay, so we try to minimize it. So which features should you use? You just have to depend on two things. One is people have written codes that if you, like I said, if you give the chemical structure, a chemical formula and the structure, it will generate like hundreds of properties for you, features for you, or descriptors for you. Okay, so there's that. Then apart from that, you also could think of some features that you need. So a long time ago, I did a work with some people to decide to know if a material was insulating or conducting. Okay. Incidentally, it's very hard to tell. If you see the chemical formula, it's hard to tell whether this material will be insulating or conducting. So of all the properties that I got from materials projects or from all the codes, one property was missing, and that is whether the number of electrons was even or odd. Okay, because I've done some condensed matter, I know that this is important. If the number of electrons in the unit cell is, in the primitive unit cell is odd, then it will be metallic. So I put that in as one of the properties. Okay, it turned out not to be the most important property. There was another property that was more important, and that property was the fact that whether it could form an ionic compound or not. Okay. So if you could form an ionic compound, then it tended to be insulating. And if it tries with all the different valence, chemical valence to form ionic compound and is not successful, then is likely not to be an insulator. Okay. That property I didn't predict. I didn't know about it, but it was one of the properties that those codes generated, and it turned out to be useful. Yeah. So two things is you depend on codes that other people have done, and also you yourself can just think about it to say, okay, what properties do I think is important? And if it's not already in the codes, you can add it to it yourself. Yeah.
Okay, thank you, Professor. There is also a question in the chat by Abu Sandal.
Okay.
Why can electronegativity difference be used as a descriptor?
Okay, yeah. So so the reason is not electronegativity difference, the range. So if you have a system that's ionic, then very likely all the electrons are in place and there are no free electrons. So like sodium chloride is insulating, right? There are no free electrons. The sodium already gave up its electron to the chlorine. Chlorine already took the electron, and they are bound by Coulomb interaction, and so there are no free electrons. So if there are no free electrons, then it cannot be metallic, right? The band gap will be 0. If there are free electrons, if there are no free electrons, then the band gap will not be 0. Okay, then it's insulating. And then, so if you have two different elements in the compound, and there's a light difference in electronegativity, then it's likely to be ionic. And then if it's ionic, you expect it not to be metallic. So the band gap, you should have an appreciable band gap. Okay, so you expect that the more appreciable the band gap, the more insulating it will be. Okay, this is just simple thinking without digging too much into it. Yeah, and if the electronegativity difference is small, let's say they're the same, fluorine, then you expect that it may be, well, not fluorine. So sodium, for instance, then you expect that it may be, it will not be ionic, and then it will not be ionic, then it may be metallic. Okay. But having said that, another property that I think is important also is the valence. Okay. Because for fluorine, for instance, fluorine is going to be insulating because it's going to form the fluorine dimer. So you need to couple it with another property, very likely the number of valence electrons, to be able to know whether it's ionic, whether it will be insulating or not. Okay. And yeah, so if I show you this data, you'll see that it's not really smooth. Oh, there you go. The experimental band gap and the electronegativity range, all the points don't fall in a straight line, right? Okay. So the points don't fall in a straight line, so it's hard to say, but you can just see that there's an upward trend, that as the electronegativity range increases in general, the experimental band gap increases. What about this point? The electronegativity range is exactly 0, but the band gap is high, almost 6, right? So there are things like that the experimental band gap versus the electronegativity range does not explain, or like a point here or a point here. Okay, but in general, there seems to be an upward trend. Okay, and then so it's not something cast in stone. There are other properties that come into it. So it's multimodal. Yeah. So this is what I will say, and this is what my thinking seems to assume. Yeah, Niha, do you have your hand up?
Yes, I have question.
Yes.
If the relation between the descriptive features and the output is non-linear, how machine learning dealing with this?
Oh, okay. So one way to do it is we should include also terms that are products. So I should include A8 times product of this EN mean and EN range. I should include A9 product of EN standard deviation and Z mean. I should include product of products. So quadratic terms, I should include them also. Some will say, yeah, and also you should include cubic terms. Okay, so you can do that also. And then the model becomes more complex, but this is a way to do that. It turns out that there's this trick you can use, and that's the kernel regression ridge method, that Yeah. So there's kernel-rich regression, which you can use. You choose a kernel, and I can give you references to it, and somehow it will generate different products for you. It will generate some non-linearity for you. Okay. So then your target does not depend only on the linear part, but also there's some non-linearity in it. So you can do that for non-linearity. There's neural networks also that you can use. The only problem I have with neural network is that you need lots of data. Thousands of data is not enough for a neural network. I've tried it before where because with this calculation, I only have thousands of data, even if I have like 20,000 data points. When I train and it's very good. But when I test, the test is just very bad. Okay. And I tried different layers in the neural network, but still, it was just a waste of my time. I spent like, I don't know, I want to say maybe I spent 1 or 2 days on it, trying this, trying that. Then I gave up, no. And then I spoke with an expert, or someone I think she's an expert, and they said, oh no, for neural network, you need lots of data. So then, yeah. So, well, with kernel-rich regression, that's the way you choose a kernel. A kernel helps you to find the product of two functions. Okay, there's the way you choose the kernel, and then when you do that, it adds non-linearity to your system, and you can get better results than just using a linear model. There's random forest also. Random forest uses another trick, which maybe if you do this twice, then I'll tell you about random forest. Okay. Yeah. So there are ways to include non-linearity, and is the way I will stick with now is just kernel-rich regression or also random forest. So our hands-on today, we will just do linear regression and random forest, and we'll see how good both of them are. Okay. Should we go to the
Thank you so much, Professor. For the participant, if you have a question, you can write it in the chat, or you can just open your mic and ask, raising the hand.
Okay. Let's go to the let's go here to the hands-on. So I think you should have received this Python notebook, which you can open with Jupyter. Okay. In the past, I will tell you how to open Jupyter and all that. But basically, for Jupyter, you can just go to anaconda.org and download Anaconda and install it. So I think it's anaconda.org, not anaconda.com. And you can just install it. There's the place where it should. Yeah. So you can install Anaconda. Oh my goodness. I don't know why it's taking time. Or maybe I should go to anaconda.com. I think it's anaconda.com.org, not .com. Oh yeah, maybe it's anaconda.com, and then you go to download, and yeah. Yeah, so I think you can go to anaconda.com and download the Anaconda. The good thing is that I don't know if I'm a returning user or not. Okay, you can sign up with your email, and then you can download it for your system. Okay, once you install it, one of the packages it installs is Jupyter. And so for me, I already have the Jupyter installed, so I can open this with my Jupyter Notebook. Okay. So basically, if once you open your Jupyter Notebook, you get something like this, and then you can navigate to where your Python notebook is. And when I do that, I'm able to get to these exercises. Okay. So in the notebook, it gives you something to build intuition for overfitting and underfitting. I'll explain that later. Then it helps you, it assembles a small material data set. Actually, nobody does this, but we're doing it just for the purpose of pedagogy to teach, okay? Because typically you get the data set from Airflow or from Materials Lab, or you get the data set from Airflow or Materials Project. So you already get the data set. So in this case, we designed the data set. Okay, so there's a data set. You will see the data set just now. And then we will train and compare two machine learning models, linear regression and random forest. And then we'll see how to do feature importance. And if you want, you can also try the data learning model. Okay. So it turns out that for machine learning is basically Python. So it's good to learn some Python. You need to import a few libraries. You need numerical Python, so we import it. Typically, you need pandas because pandas, you use it to read your data, manipulate your data. Okay. And then if you want to plot, you will typically need matplotlib. Okay. Okay. Then in this training, we're using sklearn to do many of the things that we're doing. Okay. Of course, you need to split your data, so you import train test split. Okay. Then we'll do a linear regression. Okay. And then we'll do random forest. So even the ones that we don't need, it was imported. You may want to scale your features. Okay, so we have that. So the first thing we do here is just to see what happens when you put too many parameters in your model. Yeah. So you can have too many parameters in your model and not enough data. So it's possible to have that. Okay. So the way we will show this, and then is we are going to first generate the data. So in this case, the data is not given to us. You first generate the data. Okay. This is just a test, not a test. This is just to teach. Okay. So we first generate generated data. Okay. And this generated data consists of a function that we added noise to. So that's the generated data. Okay. And then we are going to try to develop a model to reproduce the results of this data. Okay. So we will train the data. Okay. So let me explain this line. So in this line, you split. So X is your features. Okay. And Y is the target. Okay. But you split X and Y. Okay. And you split it so that the test is 30% of everything and the training is 70%. So you put this test size there at 0.3. This random state, you can put any number there. It just helps you so that the next time you repeat, it does the same thing. Okay. Because what you find out is when you're doing the calculation, you make errors and you have to repeat certain parts. And this random state just helps you to make sure that each time you repeat, you get the same result. Okay. So what does this train test split do? What does it do? It splits your data, XY, into two sets. One is your training set, okay, and the other is your test set. So it splits X into training test, and then Y into the corresponding training and test set. So it does the split for you. You don't have to split it by hand. here we just plot the training and the test set. The training we plot with blue dots. The test we plot with X, red X. Okay. And then this is the data. The true function is here. We added noise to it to get the blue and the test X data. So this is the data. And then we want to predict this data, okay, the true function. We want to predict it using a polynomial. So we are going to assume that the prediction is a polynomial of degree D. Okay, so we are going to say y is a naught, and another one is y the predicted or model is a naught plus a1x. Another one is a naught plus a1x squared. Sorry, a1x plus a2x squared, and on like that. Okay, so we are going to predict, use degrees from 1 to 15. Okay, and we are going to make prediction for each polynomial degree. Okay. So here, what this does is it fits the model. Okay, and then it calculates the mean absolute error of the training and the mean absolute error of the test. Okay. And so when you run it, the way you run it is you can press this arrow, which is to run, or if you like you can press shift return and it will run it. So when you run it, you get something like this. So what is shown here is the mean absolute error for the training set and for the test. So you see, as you add more parameters to the model, as you add more terms to the model, the mean absolute error drops for the training. Okay. So the training data is data that the model saw. Okay. What about the test? The test data is the data that the model never saw. Okay. So at first the training data keeps reducing because you are finding the best A0, A1, A2, blah, blah. And you keep finding better and better. I mean, when you add more degrees or more polynomial powers to your polynomial, you make it longer and longer, you get a better fit. You keep getting a better fit. Okay. But look at what is happening to the test. At first, the error of the test is reducing up to like 6. After 6, it starts increasing. Okay. So what does that mean? That means you don't have enough data for your model. So here we call it overfitting. So your training is doing better and better, but your test is doing worse. So this is an overfitting. So the best place to stop is to have a model with degree 6. So A0 plus A1x plus A2x squared up to A6x to the 6. That's the best way for this model with 30 data points. Okay. Beyond that, you are overfitting. The absolute error of the training will keep going down, okay, or stay the same, but it will not go up. But then the absolute error of the training starts going up. So here at 6 is the best place to stop. Okay. So while you may want to get a better model by adding more parameters and adding more descriptors, you have to be careful about this. That you have to be checking how the accuracy of your test and then stop when you need to stop. Okay. So this question asks, this exercise asks the question like this. Try to do the other things about the exercises. Okay, so let's do a practical one related to band gap. Okay, so first we build a small data set of well-known semiconductors and insulators with the experimental band gaps. Okay, so you can get this online at different places online. Okay, it's good enough to learn what we're doing now, and we store each compound as elements to geometry count. Okay, this data that I'm showing you, I show for all the elements of the periodic table, hydrogen. I put their atomic number here, the electronegativity, Pauli's electronegativity, the covalence radius in parts per million. Okay, so this is basically, this 3.1 is basically 0.31 angstroms. 1.28 is basically 1.28 angstrom, and then the number of valence electrons. Hydrogen I put 1, lithium I put 1, boron I put 3, and on like that. Okay. Okay. So this data, most likely you will not see it. It's already in PyMagen or some other people's code, so you typically not see it. They put this for all the elements of the periodic table. Now, our data, where's our data that we want to fit? So here we put the band gap of the different compounds. For silicon, the band gap is 1.12. For germanium, is 0.67. For diamond, is carbon. Is C1, the band gap is 5.46. For silicon carbide, there's 1 silicon, 1 carbon, the band gap is 2.36. Gallium arsenide, gallium. So this will be our target. We are going to feed this elements, their stoichiometry, and also the band gap. So this will be our target. So if you go down, yeah, we do also for Cu2O. So there are 2 Cu and 1 O. So if you want to calculate the electronegativity, mean electronegativity, it will be twice the electronegativity of copper, plus 1 times the electronegativity of oxygen divided by 3. That will be the mean electronegativity. So it's important to know the stoichiometry. This is a simple model, so we don't even include the structure in it. Okay. And we have 44 compounds, and this is what we want to use as a target. Okay, our training model, our training data set. Still, we are going to split our training data set into 2 parts. Okay. Yeah, we're going to separate it into 2 parts. So the first thing we'll do is I'm going to featureize all these compounds. Okay, we are going to get features. Which features are we getting? The first one we are getting is the mean electronegativity. We are going to get it. We are getting the maximum. Sorry, we are getting the range of the electronegativity. We are getting the standard deviation, the mean for atomic number, the mean for radius of covalence radius, the mean for the number of valence electron, and this just tells us how many elements are in the compound. Okay. So this is what this does. It just featureizes. At the end, we're going to have a data frame that has the mean electronegativity, the range, the standard deviation, the mean, and all this. Okay. If you want, you can print the first 10 elements. This is what this df.head does. Okay. So it prints the first 10 elements. First 10 compounds. Okay. So, and then it prints the mean electronegativity, the range, the standard electronegativity, and all this. And then, of course, the band gap is here, which we took already. So these are the first 10 compounds in the list of 44 compounds. Okay. So the featureizer calculates all these properties for us. And the band gap, we just added to it because it's already in the data. Okay. So the plot I was showing you before was to see whether the band gap correlates with the electronegativity difference. Okay. As chemical intuition will suggest. Okay. So if you do it, you get a plot like this, and it seems to correlate. Like the higher the range of the electronegativity, the higher the experimental band gap. Okay. It's not all the cases. There's this case also where it's exactly 0 electronegativity, but you have a high band gap. But in general, it seems as if there's an upward trend this way. Okay. So, so here we do a correlation table. So we put the range of the electronegativity and the band gap, and you see there's a 0.7 correlation between the range of the electronegativity and the band gap for these materials. Okay, so this accords with what you see in the plots. And so there's a code here. Yeah, this .core calculates the correlation between the range and the band gap. So there's a correlation of like 0.7. Okay, the maximum correlation is 1, so there's a correlation of like 0.7. Okay. You can, okay, there's an exercise for you. You can add a new descriptor like composition features. You can add it to it if you want, or the range of valence, electron count, or like I said, you know, if you want to add whether the number of electrons is even or odd, you can add it to it also. Okay. So we'll first do the fit, which is linear regression. Okay. So again, you split the data into train and test set. Okay. So there's a training set, there's a test set for the features. There's a training set, there's a test set for the features also. The features we use are just these ones. Okay. So we omit the band gap from the features because the band gap is not a feature, it's a target. And then for the target, you have only the band gap. So you take the values of the band gap. Okay. And you split the data like this into training and test. And after that, we fit a linear model. Okay. Well, we've used linear regression. Okay. And then we make a prediction using our test set. So you fit with the training set, that's this line. And then you test with the test set. That is the next line. Okay. Then we are going to plot the prediction from the linear model against the band gap from the test set. Okay. Then also we do a random forest also. It's more or less the same, but we use the random forest model. So if you look here, we use the random forest regressor. The number of estimators, I think that just tells you how many times it should go through the random forest procedures. I don't remember exactly, but I think this was what I remembered from it. That is the number of times it should go. It should try this random forest thing, and then it finds an average for you. So it does the fit here. Okay, this is the training. So when it says .fit, it means it should do the training. Okay, it does the training here. And then again, you take the test set and you use your model to make a prediction. So you see here, you make a prediction using your test features. Here you made a prediction also using your test features. Okay. And then for both of them, we are going to check our prediction. So for the linear, so you do shift enter, or you press this, or you press this, which I already did. Okay. For the linear regression, the mean absolute error is 1.15 electron volt, and R squared is 0.24. So it's really not a good model. Okay. Random forest does better. It gives a mean absolute error of 0.92 electron volt, and R squared is 0.46. Okay. And then we can plot the prediction against the correct value. Okay. So the blue is the linear regression. The orange is the random forest. If you have perfect model, everything will fall on this dotted line. So if you look at it, the true is so this is the scatter. So you can see that the linear regression, if you eyeball it, seems to do worse than the random forest. Random forest does a little better. Okay. If you want, you can just look at this MAE and the R squared. So linear regression has a mean absolute error of 1.15, Random forest has 0.92. So random forest does a little bit better. You can, yeah, there's some exercises that you can do. And you can try another model. SVR, I don't think SVR will be good on this model, but gradient boosting regression may be good or comparable to random forest. So you can try different methods. And here, okay. So the next thing is we want to see whether we want to look at the importance of the features. So once you do the model, like the random forest model, not the linear regression model, but the random forest model, it will give you what is called feature importance, and this is code to be able to plot it. So when we plot it, we see that standard deviation in the electronegativity is the most important feature, okay, followed by the range in the electronegativity. So the standard deviation seems to be more important than the range of the electronegativity. And then here's your feature importance. The number of elements seems not to matter. The mean of the number of valence electrons seems not to matter. The most important thing seems to be the standard deviation of the electronegativity. Okay, so it gives you the values that was plotted up there. The next thing is, finally, we try to do delta E learning. So you fit the difference between the true result and the cheap method. So the cheap method that we use here is the linear regression. So it's not like we have another model, but we use the linear regression for our cheap method. Okay. And then on top of that, we now use random forest, okay, to develop the correction. Okay. So this is the code for it. So let's look at our results at the end. Yeah, the data learning produces a better RMSE than if you just use direct random forest. Direct random forest, if you remember, it was 0.92 electron volt. If you use data learning, you get 0.7 electron volt. The data set is small, but I think this is a good place to start from. Okay. What I wanted to do also, yeah. So here also, instead of plotting the electronegativity range, we could have plotted the standard deviation and probably get a better result. So let me do that quickly. So after I do that, then I'll leave you to experiment on your own. Okay, so I do this. What is the standard deviation? What's it? std_in. So if what the feature importance tells us is correct, then we should have that the standard deviation should fit better with the electronegativity. I just write it as standard deviation. Okay. That's the standard deviation of the electronegativity. And then we also do okay, so okay, so let's see how it does. It's not obvious that it is better, but the correlation increases slightly to 0.727, 0.73 from 0.7. So it seems to be better correlated, at least from these numbers, with the band gap than the range, which is 0.7. Okay. So at this point, I'll stop, and you already have the notebook, so you can try. Okay. One thing I forgot to give to you. I'll give it to you on the screen now. And that is my email address. So if you have questions, you can send me an email.
Thank you, Professor.
Okay.
For the tutorials, we already have it. We have the. Thank
Okay.
you.
So if you have questions or you need help with something with the tutorials, you can just send me an email, and I'll be happy to help you. If you really want to do something that is that you want to publish and is standard, I can guide you into how to, because you will need to install MathMiner PyMathGen, and then I can guide you into that, and also how to get the data you need from materials project, or from Airflow, or from OQMD or Jarvis DFT. I can guide you into how to get that. If you want to go further in this, so I can guide you into how to use MathMiner PyMathGen and how to get your data from materials project, and Airflow and OQMD. Yeah. Okay. So I think it would be good to stop here.
There is some question. There is a question in the chat by Abu Santan. He's asking how could the machine learning accelerate the discovery of high efficiency solar cell materials?
Okay. So the first thing you need to do is to try to write down all the possible chemical formulas that you want to use. Okay. So you can say that, okay, I want to look for all the binary semiconductors that are good for solar cells. If you are to be good for solar cell, one thing, you have to be direct bandgap material. Okay. Secondly, you have to have a bandgap of like 1.3 electron volt. I think because there's this Shortley quasar limit, and I think it's 1.3 electron volts. Okay. So those two things you need to have. And then you also, yeah. So if you have those two things, you'll be a good absorber, and then you'll be able to get a good efficiency. So first, you write down all the possible chemical formulas that you want. Not by hand, you use a code to generate all the possible chemical formulas. And then you have to build a model that takes the chemical formulas and uses the chemical formula to predict the band gap, one, and to predict whether it's direct or indirect band gap material. Okay. You want a direct band gap material, so not indirect. So you have to develop a model that will predict that it's direct band gap materials, and also a model that will predict the band gap. And then once you develop those models, you can now feed your all the data that you generated, the different binary compounds that you generated, feed them into the model. And then at the end, it will give you a list of the material, the band gap, and whether it's direct or indirect. And then you can sort it and find the ones that have band gap of 1.3 like you have, like you want, and choose the ones that will likely give a band gap, that will likely be direct band gap material. Then one thing you need to do is you need to check that these materials, you can synthesize them and they're stable. So then you need to either develop a model that will check that they're synthesizable and they're stable, or you can just use a model that somebody has developed already. Okay. So I think that people that have developed models that you can use to check whether it's synthesizable or and also predict the energy. So there are models that can do that. Even there are models that can already tell you whether it's direct or, sorry, that can tell you whether it's predict the band gap. So you can use models like that. I'm not sure if there's a model that can tell you already whether it's direct or indirect. Okay, you can check already to see if there are models that can predict whether it's direct or indirect. Yeah, so those are the steps I will take. Okay. Okay. I think there are other questions, right?
Yes, there is a question also in the chat by Muhammad. He's asking if machine learning model predicts the band gap accurately. How do we know that the relationship learned by the model is physically transferable and not a statistical correlation? So
Okay.
he has two questions.
Okay. So from my experience, I will say that from my experience, I will say that machine learning models are able to predict the band gap of materials at least up to 0.2 electron volts. Okay. Although in that case is delta E machine learning. So what in that case I did was I calculated the band gap from a semi-empirical method, DFTB. Okay. And then I found the difference between the DFTB result and hybrid DFT result. Okay. And then I modeled this difference. So anytime you give me a system to say to calculate the band gap, I'll just do the DFTB calculation, which is semi-empirical, and I'll add my machine learning correction to it. And I was getting results that were like 0.24 electron volts, or let's just say 0.2 electron volt error. So I think up to at least 0.2 electron volt, you can trust that this thing works. The other thing that you asked is, how do I know it's not just statistical correlation? Yeah, that is it like if I use it for a different system, will it work? This one is hard to know. The only thing you can do is like maybe use more data and use more data and use more data. And as you increase your data set, if it holds up, then you can think, okay, this is probably good to use. So it comes from experience. And also in this case, yeah, you can just add more data and see how well it does. Yeah. So I would say there's no guarantee, but you can keep adding data or testing it on different systems and see how well they do. Yeah.
Okay, thank you. There is also another question by Abu Sandal. How would you combine experimental and DFT band gap data?
Okay, this is a good question. I think the best thing is to keep them separate and not combine them. So it's good just have your data set of experimental band gap and not DFT band gap. Okay, sorry, and not add both of them together for your training. Okay, and then you can now train the difference between DFT and the experimental band gap. Okay, that difference you can train it with a machine learning model, so that each time you use DFT to do a DFT calculation, you use your machine learning model to calculate the correction, the difference, and you add it to your DFT results. And hopefully that will very likely give you a result close to the experimental value for that material. So I'll say, yeah, you keep your data separate. You fit the difference between machine learning and DFT, between the difference between the experimental result and DFT. You fit the difference, and that will be your model. So anytime you do a calculation with DFT, you just add your model difference to it, model correction to it, and that should give you a result that's close to the experimental result.
Okay. I also have a question on this. Is it better to train on the experimental or on the DFT? Because the experimental is more, let's say, the accurate or the exact, not exact with some degree of error, but it's the accurate values.
Yeah, so it's always better to train on the experimental results. Yeah. The only issue now is that we don't have as many experimental results as we want. Experiments are more difficult and there are a limited number of them. So I think in this respect, a better way is if you can generate a lot of GW results, then I think GW results are closer to experiments, and then we can now use GW results more often. Okay. So I think this will be the way to go, because like I said near the beginning, you can, while we are here or at the beach or something, we can have our computers calculating GW results from any compounds, you know. Experiment, no, you can't do that. You have to be there, at least for now. Maybe later somebody will have a way to automate experiments, but still that will be difficult because first you have to synthesize the compound and then give it to somebody to determine the band gap. Whereas for computational GW results, you just get the structure, which is already available online, and you just do the calculation. So I would think a good way to do is to have an army of people to say, okay, let's calculate band gap for GW band gap and just calculate it. I'm almost sure that there's someone that's already doing this, like some group in Europe or the US that are just using their computers to calculate the GW band gap for materials. So yeah. So I think this would be a good way to go.
Okay, thank you. If there is another question from the participant in the chat, okay. So the answers are clear for the participants. Thank you so much, Professor Omololu. It was an honor and pleasure to have you today. And the lecture was really nice, enjoyable, especially for me. Now I'm entering this field of machine learning.
Oh,
So,
that's good.
yeah.
Yeah.
Thank you so much.
Yeah.
For the
Thank you very much.
You are welcome.
Yeah.
For the participant, we will have the tutorial at 4. We will send you the files to just try to run it and start getting familiar with it. And at 4, we will discuss. Okay, thank you, everyone. Have a nice day. Yeah.
Thank you.
Bye.
Thank you, Prof. Thank you, everyone.
Thank you.
Okay.